last time we looked at some finance questions where it was like you have this much to invest at this interest compounded in this way, and then how much would you have in the end. But I do want to look at some problems today that maybe we switch around what the unknown quantity is. So let's look at one like that, where maybe what we know and what we're trying to find is different from what we did last time. So I want you to find the amount originally invested if you have exactly $12,384.58 after 10 years of 7% interest compounded continuously. So we do always need to round numbers to the nearest penny. We talked about that last time. Okay, so it's super important that you are accurate with money. All right, so I'm going to go through and underline kind of the significant parts of this problem. The first one is it's mentioning that we need to compound continuously. Okay, and then it's also asking to find the amount originally invested. Okay, in other words, what's it asking you to actually find? It's asking you to find A this time. Okay, and then which formula are we going to use because of the word continuously? Yeah, we're going to use the PERT formula. So remember that looks like A equals P times E raised to the RT power. Okay, so let's plug in what we know. $12,384.58 is not what we started with, right? It's what we ended with. So where should that go in for? And actually, we're not finding A. I wrote that down wrong. What are we actually finding? P. Last class, we were finding A a lot. So we're going to plug in 12,384.58 on the left side. We don't know what P is, so we're going to leave that alone. Okay, and then we have E raised to the what? What's the rate written as a decimal? 0.07, not 0.7, right? That would be 70%. So 0.07 times 10 becomes the exponent. Okay. All right, so what I don't want you to do is round a bunch of times in the middle of a problem. Okay. So I want you to just realize that E to this blah, blah, blah power is just a number. Okay. So we have P times an ugly number, and I'd rather not have that ugly number, right? So what's the opposite of multiplying? It's division, right? So I'm just going to divide by the entire E term. Okay, why do you think I don't want you to go ahead and figure out what the decimal is for this? Yeah, we want to plug it all in at once. Okay, if you round multiple times in a problem, you are most assuredly going to have errors. Okay, and we want to avoid, especially with people's money, as little errors as possible. Okay, so I want you to know that this is just a number. It's just a really ugly decimal. Okay, so we're going to leave it alone. You can also use the answer button on your calculator if y'all ever use that. If you look real quick while you're kind of writing that down, the answer key if you're using the TI is right here where the negative sign is. Okay, and what it does is it pulls in the previous answer in its entire form rather than giving you a shortened decimal version. Okay, so I'll show you how to do both, but let's do it the way that we kind of wrote it first. Okay, so we're going to take 12,384.58, and we're going to divide it by E raised to a power. Okay, if you have an older calculator, you might need to put parentheses around the exponent, but notice mine opens up a little flashing box where the exponent is, so I'm just going to enter in 0.07 times 10. So notice, if you wanted to, you could go ahead and work out what 0.07 times 10 is and just put that number in for the exponent, but it's not necessary. The calculator will do it all if you'll just punch it in correctly. And so when you press enter, notice that you get pretty close to what? We always round to the nearest penny with money, right? So you end up getting about $6,150. Okay, notice there is a little bit of partial cents, but we always round to the nearest penny. Okay, so let me show you how you can also, if you happen to want to use the answer key, so I'm going to try to move this up so we can see the whole calculator, or at least most of it. All right, so let's say you actually entered in what the E thing was. So you said, okay, you were in the middle of the problem and you wanted to know what was E to the 0.07 times 10 power. Notice you're going to get a really long decimal because E is already ugly, right? And then you're raising E to a power, so like everything involving E pretty much is going to be ugly. So if you wanted to use that, though, then you could say, okay, I want to take 12,384.58, and I want to divide it by my previous answer. Okay, so see how that shows up as A and S? Okay, so rather than pulling in a rounded version that might not be as accurate, it actually pulls in the complete version there. And actually, just so you know, the calculator is storing more decimals than it's even showing you right here. Okay, the calculator is storing a lot more decimal places than it views on the screen. And so notice when you push enter, you actually get the same answer. Okay, so you either need to use the answer key so that you're using full accuracy, or you just need to do it in one swoop like we did the first time. Okay, so the point being, how many times should you be rounding in a problem? Only how many times? Only once, and when should that be? At the very end, yes. Okay, so I asked you this question a lot last class. So what about if I asked you what the interest was? Or at least how could I get what the interest is? This might not be one I could know. You know, the other ones we could kind of wing it and do it in our heads, right? So how would you, figure out how much of this was interest?
Subtract that from the 12,000.
Yeah, you ended up with 12,384.58, right? So you're going to subtract off 6,150 because that's the actual cash you put in the account, right? And the difference will be the extra you earned, in other words, the interest. Okay, so notice this time the interest exceeded what we started with, okay? Why do you think that is? There's really kind of a couple of reasons. 10 years is a long time, okay? That's a pretty long-term investment, okay? It's not the longest investment you can have in the world, but 10 years is a long time to put money in an account and never touch it, right? And then 7% is actually a pretty decent rate also, okay? What's the other reason, although smaller? We're compounding continuously, which is the most frequent compounding we can have, right? So that is going to provide us with the most amount of interest as we go. Okay, so let's do one kind of like that, but maybe we use a little different terminology. So I want you to find the present value of $40,000 due in 4 years at 8% per year, compounded monthly. All right, so let's underline the important part. We're compounding monthly, okay, and we want to find the present value of $40,000 due, right? So instead of this being an investment, this is more of like a loan that's due. Okay, but hopefully you can see that this quantity actually represents the ending amount. Why do you think we can say that? Bless you. That's what's actually due, right? And what are we assuming is going to be wrapped up in what's due? Not only what you borrowed, but the extra what on top of it? The extra interest. Okay, so in other words, just like the last one, we are trying to find P. So sometimes they'll use principal and sometimes they'll replace it with present value. But this time we also need to use a different formula, right? We need to use A equals the more complicated one, P times 1 plus R over M, and then to the MT power. Actually, I changed one of these. Let me remind myself what I changed. I think I changed them both to M. Yeah, I did. I had to think about it for a minute. Okay, so the 40,000 is going to go in for A. And then we don't know P, but we'll be able to know everything else. So it's going to be 1 plus 0.08. Okay, and then what goes in for M and Y? So you might need to look at your notes from last time, but what is M in general?
Well, this is mine, right?
Yeah, it's how many times per year something happens, right? So the fact that it's monthly means that M is 12. And then we raise that to the 12 times 4 years power.
So if it's once a year, it's one, right?
Yeah, if it's annually, it's 1. Yeah. If it's daily, it's 365. If it's weekly, it's 52. If it's quarterly, it's 4. Yeah. All right, so this one, kind of like the last one, is a little bit of a mess, okay? But notice that this is just a number. It's going to be an ugly one. It's going to be a big one, okay? But this is just a number, so if I don't want that thing over there, and I don't, right? What do I want to try to isolate / get by itself? I want to try to get P by itself. So we can do some simplifications if you like, but honestly, the easiest thing to do is just divide by this whole big mess that I don't really want over here. So if it makes you feel warm and fuzzy, you can do some simplifications, but make sure that you're not rounding in the middle. So in other words, if you want to change 12 times 4 exponent to 48, you can do that. If you want to figure out what 1 plus 0.08 over 12 is, as long as it's not a repeating decimal, you can do that too. Okay? But my suggestion is just do it like I'm doing here, where you just let the calculator handle the mess. Okay, because the calculator is well equipped to do it. So we're going to get 40,000. Make sure you use parentheses, but it's 1 plus 0.08 divided by 12, and then raised to the 12 times 4 power. Maybe not every time, but I wanted you to get out your calculator because I actually want you to be punching these in too, okay? Maybe you don't have time to, when you're writing notes, to do every single one with me, but I want you to try them, at least one of each type as we go. So before I press enter, what kind of answer are we expecting compared to 40 grand?
Lower.
Lower, right? Because 40 grand is what we ended up with, right? So we're expecting something lower. Okay, so if you don't get something lower, then you know something's up. And so when you push enter, you'll get the answer, which is $29,076.82. Make sure you round to the nearest penny. Don't just drop it off after 2 decimal places. But notice this one wouldn't round up, right? It would still just stay 82. Okay, so again, if I asked you to find the interest, then what would you do to get it? Subtract, right? You'd take 40,000 minus 29,076.82. But the interest would be 10,923.18 if you round it. Okay. By the way, notice I did 29,000 minus 40,000 just because I didn't want to type the numbers in again. Okay, but I knew that that was actually supposed to be switched. So it shouldn't really be a negative number, and notice I didn't write it as a negative number. So that was just something quicker that I decided to do because I wanted to be lazy and not punch it all in correctly. All right, so Susie, did you see?
Yeah, I got it.
Okay. Okay. The biggest thing that I want you to kind of think about is I want you to kind of compare this to your life, because no matter what business field you decide to go in, even if you decide to change your major later on, you do need to know some things about personal finance. Okay, you're going to finance a car, you're going to finance a house, and I hope you don't get a whole lot of credit card debt, but we're going to talk about that too. Okay, but notice that the kind of investment / loans we're talking about here are what we call lump sum investments. Right? What does lump sum mean? How many times are you putting the money in? Once, right? So they're a little less applicable in my opinion, right? How are most Americans, middle-class Americans, probably going to save money? Are you going to have a chunk of $100,000 to save at one time, or how are you probably more likely to save money? like a little bit as you go, right? So we're going to talk about that too, okay? But just know that that's more complicated, right? Because that means every month you're changing the amount that you put in, okay? And every month you're getting a different amount of interest. So it's not as easy when we start talking about those types of investments. So that's why we're talking about these lump sum ones first. They're easier to handle, and then we'll move on to maybe more realistic investments next week. Okay, so let's change gears, same equations, but maybe let's change what we're trying to find. So what if I asked you to find the interest rate needed for $5,000 to grow to $6,500 in 3 years if interest is compounded continuously? So this time I have mentioned that we're going to be compounding continuously, but this time I'm asking you to find the interest rate, right? Which we haven't done any like this yet. Okay, so we want to find what variable? R, right? And we want to use which formula because we're talking about compound interest or compounded continuously interest? PERT. Okay, but what we're not going to know is the R part. Okay, so let's talk about how we're going to need maybe some different types of skills to be able to solve this. But first off, let's just plug in everything, right? What would go in for your beginning amount? 5,000 is your beginning amount, right? What's your ending amount? 6,500, so we'll put that in too. E is just that 2.718 blah, blah, blah number. Okay, so nothing ever goes in for E. And then I'm going to leave R alone because that's actually what I want to find. And then I'm going to multiply by 3. Okay, so where do you notice that the variable that we're trying to solve for is this time? Like where is it located? In the exponent. Okay, so we're going to have to think about how we have solved for that in the past week or so. But first, let's get it by itself. Okay, so first I would need to move the 5,000 over. You can reduce this fraction, but don't give me a decimal here unless it's a nice decimal. So I just leave it as 6,500 over 5,000. Okay, again, the only time you would be allowed to simplify that would be if it comes out nicely. I think 6,500 over 5,000 actually does, but I just always leave it just as it is. Just make sure you're not rounding. All right, so now what? Like, how do we handle an R in the exponent spot? It's kind of untouchable where it's at right now. Okay, so you have to think back to, actually the homework that's due tonight covers some of this. So do you remember what we do? So I'm going to rewrite it because we're going to do something to both sides. Remember in algebra, you're allowed to do anything you want to one side as long as you do what? The same thing to the other side, right? So what is the opposite of E? How can we undo the E part? Natural log, right? So I'm going to not multiply by natural log. That's not a thing. I'm going to take the natural log. It's like an action. It's a verb. Okay? Take the natural log of both sides. So I need to take the natural log of this side too. So what's the power in me doing that? Yeah, the ln and the e cancel each other out, and the power rule of exponents says, hey, you can move that guy around to the front, or the power rule for logarithms, I mean. Okay, so on the right side, you actually just get 3r, and on the left side, you still have this ln thing. Okay, and again, we're not figuring out what that ln thing is because it's going to be a decimal, and we only want to figure the decimal slash round it one time. So I'm actually almost there. Now what? Yeah, I just need to divide by 3 so that I get r all by itself. So I end up getting the following equation for r. I get the natural log of 6,500 over 5,000 over 3. But I'm going to want to have that in some sort of decimal slash percentage form. So make sure you're giving the answer as a decimal and then changing it to a percentage when it makes sense. So if you look at the calculator, okay, we would do ln of 6,500 over 5,000. Close the parentheses because I'm done with the ln part, right? And then I would divide that by what, according to what I wrote? Divide it by 3. And then just remember that you also still need to move the decimal place twice, okay? If you tend to make mistakes with that, you can also, rather than moving the decimal place twice, you can also multiply by 100, and then that will be the decimal that you would get, okay? So, because you need to give your answer as a percentage. So it's about 8.75%. Okay, so use the approximately, the squiggly equals when things are not equal. Okay? So notice it was 8.74, but this 5 would bump up that 4 to a 7.5. Okay, so if you were desiring to turn your $5,000 into 6,500, then that would help you decide what type of investment you would want to go after, right? A savings account wouldn't be able to get you to your goal. Okay, savings accounts don't pay anywhere close to 8.75. Okay, they hardly even pay 1% anymore. So that means you would have to seek out another type of investment if that's what you really wanted to do with your money. All right, so let's look at another one. So how many years will it take a $35,000 investment to reach 50,000 if interest is 4.75% and let's say again compounded continuously? So the significant statements are that we're compounding continuously, and it's asking you how many years it would take for that to happen. So what am I trying to find in this example? Trying to find t, and because of we are compounding continuously, what formula do we use again? Yeah, the a equals p times e to the RT power. So let's plug in what we know. So what goes where? Y'all tell me what goes where. So what goes in for A? 50,000 goes in for A. What goes in for P? 35,000. E is always just itself. What about R? What goes in for R? It'd be 0.0475, right? You can't drop off any of the digits. You need them all. Okay, so remember, if you move that twice, you would get 4.75. And then what do I put in for t, because it's my unknown quantity? T. Okay, so the first thing is to isolate the exponential term. So what do I need to do very first then? Divide by 35,000. Okay, so just to let you know, you can simplify the left side if you want to, and let me show you how you can do that, or maybe remind you how you can do that. So if you do 50,000, like if you don't like having ugly numbers in your problem, you can simplify, but notice this comes out to be a decimal, so I would not want you to use that decimal, but you can use the math fraction key and at least reduce it to a nicer fraction if that's what you want to do. Okay, you don't have to do that. I'm just showing you different options. Okay, but I would not want you to put in 1.428 blah blah blah. Okay, because that means you're rounding the answer more than one time. But you could change this to 10/7, and then at least it's a little more pleasant, right? Equals e to the 0.0475 power. So I'm going to write it again just because I like to be able to show my work. Okay, I like to be able to show you the work, really, is more likely. All right, so how do I get rid of e again, just like in the last problem? Take the natural log of both sides. So what happens to natural log and e as usual? They cancel, and this moves out to the front. Okay, so we end up getting what? So far, we're not done yet, but what do we end up having? We have natural log of 10 over 7 here, and we have the 0.0475 t here. So who cares if that's a decimal? It's that decimal times t, and I want to know what t is, so what can I do to undo that decimal? Just divide. The opposite of multiplication is always division. And then we'll just do this one to 2 decimal places as well. Okay, so if you want to work it with me, you can, but it would be the natural log of 10 over 7. Or if you never had changed it, it would be the natural log of 50,000 divided by 35,000, same difference. Okay, and then you would divide that by 0.0475. And so notice that you get about 7.5 years. If we were being really exact to 2 decimal places, you would say about 7.51 years. Okay, notice that when the answer is time, I label it with years. When it's rate, I label it with percent. When it's an amount of money, you put a dollar sign. So you always need to indicate like what unit you're using.
What if we got months? I guess it would change the way. What if the question were how many months?
If it were how many months, then you would just need to figure out how much 50% of the year is. So it'd be like 7 years and 6 months. So you would have to figure out like how many months give you that decimal. It's not going to probably do that, but that's how you would do it if it asked you. Okay, so let's look at one more, and then we're going to look at one more way that you can actually compare different interest rates together. So the last question like this is, how long does it take money to double if interest is paid at 10% per year compounded continuously? So don't let the per year throw you off. Interest is always quoted yearly. Okay, even if it's compounded less frequently, it's always quoted as a yearly interest rate. So it's compounded continuously, right? And then I'm asking you how long. Okay. Notice that this time I'm asking you to find what? T, right? And we're going to use A equals P times E to the RT power. So notice, what did I not really give you here? I didn't really give you P, okay? So let's talk about that. We can't have more than one unknown in a problem, okay? At least we in this algebra class don't know how to do that, right? We can only handle kind of one unknown quantity at a time, and we already know we're trying to find T, not P, right? So one way to do this, and I just want to show you that it actually wouldn't matter, okay? If you like, you can actually just come up with any P amount. And I'm going to show you that it actually wouldn't matter anyway. Okay, so let's just throw an amount out there to me. When y'all want to make P, we can make P anything we want. Okay, so we'll make it 10,000. Okay, so let's say P is 10,000. Okay, probably pick 10,000 because it was kind of a nice roundabout number, right? So 10,000 goes here, right? Well, what would go in A? We're trying to do what with the money? We're trying to double it, which means that what would go on the right side, or the left side, I mean? 20,000, okay? So we're going to fill in the rest, but do you see that it wouldn't actually matter what I put there, right? If I started with 5,000, what would go on the left? 10,000, okay? So let's look at why it won't matter. Let's plug in everything. We've got e to the 0.10 times t power. The reason it's not going to matter is because you're going to divide by 10,000. But it wouldn't really matter what we started with, because what would this always be? Well, not when we have the bigger number on top. This would always be what? 2, because it's doubling, right? Think about how that would be, right? If it were 5,000 versus 10,000, 10,000 divided by 5,000 would be 2 also, right? If it was 1,000,000 and we doubled it to 2,000,000, it would still be 2, right? Because when you divide it, you're still going to get 2 no matter what. So that's why it actually doesn't matter what we start with here. And so we get 2 equals e to the 0.10 times t power. And then how do we handle e one more time? Take the natural log. Remember that generally you're allowed to use either log. You can either use the LOG log or the natural log. But why do we definitely want to use natural log here? Because it's e, right? If it were not e, you could choose either form of logarithm, because frankly, either one of the logs allow you to move the exponent to the front, but both of the logs don't have the canceling property that ln does with e, okay? So ln and e go away because they're opposite operations, and so you just get 0.10t here, and then natural log of 2 here, and so one more step, what do? Divide by 0.10. You also could have said 0.1, right? Because you don't actually need the 0 after the 0.1 there. But at any rate, you're going to get t equals the natural log of 2 divided by 0.10. So let's see what that is. So ln of 2 divided by 0.10. Okay, notice we get 6.93 what? Yours?
So really, with any problem like that, we can skip the first step and just put 2 equals e.
Any problem where it was doubling,
Yeah.
you could, yeah. All right, so just a couple of things. So I want you to look at what I got for the second line, which is the correct answer. But notice, what did I do in the third entry that is incorrect? I forgot to close out my ln. So what the calculator thinks I mean, which I don't actually mean, is it's trying to find the ln of that whole thing. Like ln of 2 divided by 0.1, when I don't want it to do that, right? I want it to stop the natural log and then divide it by 0.1, okay? And notice, I'm not sure we would really kind of reason that out and think, oh, that's not a reasonable number, right? Because, I mean, about 3 years would also be kind of a reasonable number. So you just want to be really, really careful. You want to put in parentheses when maybe you don't even need them, okay? So that you don't forget them when you do, like here, okay? So when in doubt, just use parentheses is what I'm trying to say. Okay, so the very last thing that we're going to talk about today is something that if you have credit cards / savings accounts, you can actually go home and look this up today, kind of apply it. But there's something called the effective interest rate. Because interest rates are all kind of compounded differently, it can be really confusing to try to compare 2 accounts together that aren't the same terms. So it's basically an annual rate adjusted for the frequency of compounding. So it allows you to truly compare apples to apples when you're trying to compare maybe vastly different types of accounts. You will see this on your credit card statement sometimes as the annual percentage yield, or APY. Okay, and if you have credit cards, you shouldn't stick your head in the sand about them. You should read up on them. You should know what terms you have. You should know how you're going to pay it off. You shouldn't just be like, I'm just going to pay whatever it is they tell me to pay. Okay, that's not the kind of consumers that I want you to be. So here are 2 kind of versions of APY. So the first one is 1 plus R over M to the m power minus 1. Okay, this is for periodic compounding. What does periodic mean again? like on a regular time schedule, right? So it could be monthly, but it could also be things like what? Quarterly or annually or anything like that, okay? Or if you're compounding continuously, there's another one, and not surprisingly, it uses e, but it's just e to the r power minus 1. So this is for continuously compounded. So, and again, let's just write down what we use this for. We use this to compare two accounts, usually with different compounding frequencies. So remember how I said the more interest or the more times you compound interest, the more money is earned? Okay, so let's maybe recall that here, because that's really what we're talking about. So I already had you write this before, but it's a good principle to know. The more often interest is compound or figured, the more money is earned. But the question might be like, how much more? In other words, what if you're comparing two accounts where one compounds more frequently, but it has a lesser interest rate or something? Then how do you compare that to one that compounds less frequency but has a higher interest rate? Okay. So on all credit card statements, they are required to tell you your APY. Okay, the federal government requires that they do that. They probably wouldn't do it. I'm going to go out on a limb and say probably wouldn't do it if they didn't have to do it. Okay, so they make them report kind of more accurately, basically. All right, so let's see how far we can get with this one, and if we have to finish this up next time, we will. But I think we can rush through it. So which credit card is better for the consumer? So let's say card A has a 18.5% per year rate that's compounded daily. And let's say we're going to compare that to card B, which has an 18% per year rate compounded continuously. Now, for the most part, you won't see any credit cards that do compound continuously, but I just wanted to basically show you both formulas. There are other types of loans that are allowed to compound continuously. So if you were just looking at face value, which account would you want if it's a credit? Remember, you're the consumer, right? So do you want to pay more interest or less? You want to pay less, right? So which card would you pick if you were just not knowledgeable about what we're talking about today? You would definitely pick card B, right? Because it's a little bit less interest, okay? But the point is that maybe it makes up for that in the fact that it compounds more often. Okay, so we're going to find out kind of how we can compare the two. So let's look at card A versus card B. Okay, and I'm just going to show you what these are, and you can punch these in your calculator later. So the APY for card A would be 1 plus the stated interest rate, which is 0.815, over how many times a year, which is 365, and then raised to that same power minus 1. Okay, as opposed to card B, we use the E version of the formula, so it's going to be E to the 0.18 minus 1 power. So in other words, we don't really care what they say the interest rate is. We want to know effectively what we're actually paying. Okay, so if you punch this in, you actually get 20.32% here versus 19.72% here. So what do you notice about both of them? They're both higher than what they stated, right? And why are they higher than what they stated? Because they're compounding so much more frequently than annually, okay? But which card would be the best then? Yeah, so card B is better for the consumer. Now, if I'm the interest or the credit card company or the bank, I would prefer card A, right? So that's why I want to specify that we're talking about for the consumer. Okay, so what the effective interest rate / APY allows us to do is get on a level playing field. Okay, so you should be able to find that on your credit card statement, or if not, you should be able to figure it out based on what they're telling you the interest is. And then what did we already say that credit cards, usually what would be the compound frequency for credit cards? Almost always daily. Okay, so you could maybe go home and look at a credit card statement and see what you get.